A modern railway looks simple from the window, two steel rails running to the horizon. But underneath that simplicity is one of the most demanding projects in all of civil engineering. Millimeter tolerances stretched across hundreds of kilometers, carrying trains that weigh hundreds of tons at 300 an hour. This is how you build one, from an empty field to the first train, step by step. Building a railway is a sequence, and the order is everything. You cannot lay track on ground you haven't shaped or electrify a line you haven't built. The work flows through 7 great phases. First, you survey and plan. Then you move the earth. You build the structures that cross what the earth can't. You lay the track. You weld it into one continuous ribbon of steel. You hang the power lines above it. You install the signaling brain. And finally, you test everything until it's safe to carry people. Long before any machine arrives, the railway is built on paper and in software. A route has to be chosen that balances gradients, curves, cost, communities, and the environment. Teams fly the corridor with laser scanners, run environmental assessments, and negotiate for every meter of land the line will cross. Get this phase wrong, and the whole project can stall for years. The planning phase follows its own chain. First, feasibility and environmental impact studies decide whether and where the line should run. Then aircraft and drones sweep the corridor with LiDAR, firing laser pulses to build a centimeter-accurate digital terrain model. On that model, engineers refine the curves and gradients. Only then come the regulatory approvals and the slow, expensive work of buying the land and clearing the right-of-way. And this is where time disappears. A well-run project on open terrain, like Spain's Madrid to Valladolid line, can go from plan to service in about 6 years. But add difficult geology, legal disputes, or environmental objections, and the same distance can take 15, 25, even 40 years. Nothing about a railway is slower than deciding where to put it. With the land secured, the earth movers arrive. The first job is brutally simple. Reshape the ground so it matches the gentle gradient a train needs. Hills are cut down, valleys are filled up. But hidden inside that simple idea is some of the most careful accounting on the whole project. It's called cut and fill, and the goal is balance. Engineers try to make the volume of earth cut from the high points exactly equal the volume needed to fill the low points, so nothing has to be hauled in or carted away. Software sorts the excavated material as it comes out. Strong rock and gravel go into load-bearing embankments, while weak soils are diverted to landscaping. A perfectly balanced line barely moves a cubic meter off-site. But raw earth is not strong enough on its own. Under the pounding of repeated train loads, weak ground settles unevenly and tears the track out of line. So engineers build the ground up in engineered layers. Weak clay is mixed with lime or cement to stiffen it. Polymer geogrids are locked into the crushed stone layers to stop them spreading sideways. A geotextile sheet separates the clean ballast from the soil below, and a network of drains carries water away, because waterlogged ground has almost no strength at all. Sometimes the ground simply refuses to cooperate. A mountain in the way, a river, a deep valley, a city. Where the railway can't follow the land, engineers build structures to carry it straight through or high above. These are the most expensive kilometers on any line. Tunnels are the hardest of all. In soft ground, a tunnel boring machine grinds forward, erecting a ring of precast concrete segments behind it as it goes. In hard rock, crews drill and blast. The constant enemy is water, which floods the face and can be held back only by grouting or even freezing the ground. And every finished tunnel hides its own safety world. Escape cross passages linking twin bores, jet fans to clear smoke, waterproof membranes, and concrete laced with polypropylene fibers so it won't explode under the heat of a fire. Where the line must fly over a valley, it rides on viaducts, rows of tall piers carrying pre-stressed concrete box girders, poured or launched span by span. And where a slope threatens to slide onto the track, engineers build mechanically stabilized earth walls, layers of compacted fill locked together with steel strips and geogrids, strong enough to hold back a hillside. Every one of these structures has to carry a moving train for 100 years. Now, at last, the track itself. And a railway track is not just two rails, it's a carefully engineered stack. At the top, steel rails carry the wheels. Resilient clips fasten them to concrete sleepers. The sleepers sit in a deep bed of angular crushed stone ballast, which grips them and spreads the load. Below that, a subballast layer, then the prepared subgrade. Each layer passes the enormous point load of a wheel down to the earth, spread wider and gentler at every step. There are two ways to build that stack. Ballasted track, rails on sleepers in crushed stone, is cheaper to lay and easy to adjust. A tamping machine can re-level it anytime. Slab track sets the rails on a continuous reinforced concrete slab instead. It costs far more upfront and can barely be adjusted once cast, but it holds its geometry for decades with almost no maintenance. High-speed and tunnel lines increasingly choose the slab. For long, open stretches, the track is laid by a machine that works like a moving factory. A track construction train, such as the Placer and Tire SVM 1000, advances continuously, building the railway beneath itself as it goes. A gantry crane on top passes concrete sleepers forward and drops them onto the prepared bed at exact intervals. The rails are threaded in from the sides, and a hydraulic clipper fastens them down. The track is literally born from the front of the machine. The process runs in 3 steps. Place the sleepers, thread the rails, clip them tight. Where the machine can't reach, at switches or inside tunnels. Pre-assembled turnout panels weighing up to 240 tons are carried in and set by remote-controlled gantries. Then hopper wagons pour the top ballast, and heavy tamping machines lift, align and pack the stone beneath every sleeper until the geometry is perfect. Rails arrive in lengths, but a modern railway runs on one continuous ribbon of steel with no gaps, because every joint is a weak point and a source of wear. So the lengths are welded together. Flashbutt welding is the workhorse. A machine clamps 2 rail ends, passes a huge current to melt them, then forges them together under pressure. A clean joint at nearly full rail strength. Out on the line, where a machine can't reach, crews use thermite welding, a chemical reaction that burns at around 2,500 degrees, pouring molten steel into a mold around the joint. But continuous rail has a hidden danger. Steel expands in heat and contracts in cold. Welded into one piece, and a hot summer could buckle the track sideways, while a freezing winter could snap it in two. The answer is the rail neutral temperature, the temperature at which the rail is set to have zero stress, chosen as the midpoint of the local extremes. Crews stretch or heat the rail to that exact length before clipping it down, locking in a track that's calm in both summer and winter. An electric train draws its power from wires strung above the track, the overhead catenary. It's a suspension system in miniature. A messenger wire hangs in a gentle curve between masts and carries the weight. Below it, held dead level by vertical droppers, runs the contact wire that the train's pantograph actually touches. Automatic tensioners, counterweights hanging at the masts, pull everything tight and keep the tension constant as the metal expands and contracts with the weather. And the tension matters enormously, far more than it looks. Simulations show the system leans on the messenger wire. A 10% loss of tension in the lower contact wire barely moves it. But just a 5% loss in the messenger wire above lets the whole assembly sag by around 20 millimeters, because that upper wire carries the dead weight of everything. And even a small sag makes a 300 km/h pantograph bounce, arc, and lose contact. Constant tension is everything. With power in place, the line needs a brain to keep trains apart. The old way is fixed block signaling. The track is chopped into fixed sections, and only one train is allowed in each block at a time. Safe, but wasteful, because the block is sized for the worst-case stopping distance. The modern way, ERTMS Level 3, throws the fixed blocks away. Instead, each train carries a moving safety bubble, calculated in real time from its exact speed, position, and braking power, so trains can safely run much closer together. Making that work takes a tightly linked system. On the train, An onboard unit fixes its position using satellites, while sensors and radar, and constantly checks the train is still in one piece. Passive beacons called euroboluses, bolted between the sleepers, recalibrate its odometer as it passes. A radio block center talks to every train by radio, handing out movement authorities permission to proceed. And underneath it all, the interlocking makes sure two conflicting routes can never be set at once. Everything is built, but nothing can carry a passenger yet. The final phase is testing and commissioning, run by an independent team so that safety never bows to the construction schedule. Its most dangerous moment is energization, the day the site stops being a construction zone and the overhead wires go live. It's planned for months, with formal notices, isolation diagrams, and a rulebook that changes everyone's site pass from white to yellow. Testing marches through a strict order. Equipment is proven at the factory, then retested once installed on site. A release notice hands each section to the commissioning team under lock and key. The power is switched on. Then real trains roll. First at a crawl, checking clearances and brakes, then faster and faster, verifying track geometry, pantograph contact, and signaling under full load. Only when every test passes is the line handed to the operator, who runs empty trains to train the staff before the very first passenger ever steps aboard. And that is how an empty field becomes a railway. 7 phases, each depending on the one before: survey, earthworks, structures, track, welding, power, and signaling. Then tested until it can be trusted with human lives. The next time you glide along those 2 simple steel rails, remember the decade of engineering hidden beneath them. If you enjoyed this, stay with us. There's a whole railway still to explore.